Now, let us consider some various combination of heat resistors. So, here we have a configuration Y configuration. So, this side length L, this is of length L, this is of length L and this is of length L. All the rods have thermal conductivity K and they have all the same area of cross section A. Now, the rod AB, A is maintained at T1 temperature, then this BCF portion. So, this F is maintained at T3 temperature, BDE of which the end E is maintained at T2 temperature. At steady state, what is the temperature TB that has to be found? So, we have to find the temperature at TB. So, what we do at steady state, let us since T1, T2, T3 are just symbols, I assume that suppose this is at higher temperature than this and this is again at higher temperature than this. So, heat flows through this is I1 and heat flowing through this rod is I2 and so finally, heat flows from this is I3 which is the sum of these two and let this temperature be TB. So, now consider, so we have to find the temperature TB. So, what we do? Consider the heat flow, steady state heat flow through the rod BCF. So, the heat current I1 is given by conductivity A into temperature difference, that is T3 minus, suppose I say TB is T, by this length. Total length is L plus L by 2, that is 3L by 2. This is equation number 1. Similarly, I will consider EDB rod. So, consider the heat flow through the rod BDE, this rod. So, the heat current is I2 that is equal to K A, the temperature difference T2 minus T by again the length 3L by 2. So, this is 2. Now, the heat flow is I3. So, consider the heat flow through the rod BA. So, this is I3, this is K A, this is T must be higher. So, T is higher I have assumed, minus by total length, that length is L. At steady state, I1 plus I2 must be equal to I3. So, you add up 2 Ka T3 minus T by 3L plus 2 Ka T2 minus T by 3L is equal to Ka T minus T1 by L. So, this L Ka cancel. So, we have 2 T3 minus 2 T plus 2 T2 minus 2 T and this 3 is multiplied here, 3 T minus 3 T1. So, let us bring all T's this side and all 3 T1. So, here 2 T3 and 3 T1 will be brought here, plus 2 T2 is also there, 2 T2 is also there, then plus 3 T1 becomes equal to this 2T, 4T and plus 3, this is 7T, implies T is equal to 2, T T2 plus T3 plus 3 T1 by 7. This is the temperature of B. So, now take another case of a combination of thermal resistors, and we will see how to analyze it. So, here there is A, B, C, D, E, F, G, these many conductors or rods are there, each having the same cross section area, length is also the same, but conductivity is different. This is K naught, here K naught, here 2 K naught, here 2 K naught, 3 K naught, 4 K naught, 5 K naught. So, you see here the ratio of these two conductivities is same. This is K naught by 2 K naught, K naught by 2 K naught. So, it forms a Wheatstone bridge. So, let us come to what is a Wheatstone bridge. We will see first electrical part. So, in electricity we have seen that if this is R1 and this is R2 and we have R3 and this is R4. So, if we have 4 resistors arranged in this manner, and suppose here there is R5 or something, or suppose here we have a galvanometer, then if R1 by R2 becomes R3 by R4, then there is no reading in this galvanometer. That means these 2 points are at same potential. We have already seen that a heat conductor has its equivalent thermal resistance. That means, if I have again the same case with this heat conductors R1 by R2, that is equal to R3 by R4, then again this point and this point will have the same potential in electricity, which I will call the same temperature. And so, if you connect it with a wire, there is a conducting rod, then no heat transfer takes place. So, here thermal resistance RTH is equal to L by Ka. So, La is same. So, the ratio, this is here K naught by 2 K naught and here K naught by 2 K naught. So, here R1 Ra. So, thus here Ra, that is the thermal resistance Ra by Rb is equal to Rb Rc by Rd. So, it forms a Wheatstone bridge arrangement. So, the bridge is balanced, and so and thus no heat flows through F. So, this rod, the heat current, there is no heat current through this rod. So, you can remove this, they are at the same temperature. Now, let us see that in order to maintain this temperature T1, how much heat has to be supplied. So, you see this rod takes heat from this end and delivers through this, and you see this F is of no use. I am removing this because it is of no use. So, I have removed this F because these 2 points are at same temperature now. So, what happens now? So, now you can see this heat flows, heat current is I1 here and I2 here, and the heat I2 flows here and the heat I1 flows here. So, these two conductors are in series and thus heat flows through this. Let us see what is the temperature of this. So, this is K naught and this temperature is T, this is here T1, heat current I1 flows, this is T2, heat current I1 flows, and this is 2 K naught. So, you see, let us see the heat equation here. This is I1, that is equal to K naught, this area of cross section A. Suppose T1 is more, so heat flows here by L. Similarly, here this I1 is equal to, this is 2 K naught A, temperature T is higher than T2 and so by L. So, these two are equal. So, let us equate it. So, we have K naught A, K naught A, L, L. So, we have T1 minus T is equal to 2T minus 2T2 implies this 2T T1 plus 2T2 by 3 is equal to T. So, we have the temperature as T is equal to T1 plus 2T2 by 3. Now, let us see what is the net heat transferred through combination of these two. So, we can use directly the formula for heat the series and parallel combinations. So, let us use this. Suppose this is R1, R2, R3, R4. So, we have this combination as R equivalent, they are in series. So, in series R equivalent is R1 plus R2. So, that is R is equal to L by K naught A and this is equal to L by 2 K naught A. So, L by K naught A common, 1 plus 1 by 2 is 3 by 2, just write 3 by 2. For this route again the same situation. So, again R equivalent will be the same. So, now this and this are in parallel. So, we have R equivalent for this is, so we have this as suppose R1, let us call this as R. So, this is 1 by R equivalent is equal to 1 by in parallel 1 by R plus 1 by R, that is 2 by R, implies R equivalent is equal to 2 R. This is R by 2, this will be 2 by R. So, R equivalent is equal to R by 2. So, the heat current I1 plus I2, that is I total is equal to the difference, that is T1 minus T2 by R equivalent, the total R equivalent, that is equal to R by 2, that is 2 T1 minus T2 by R. Now, what is R? R is 3L, R is 3L by 2 K naught A. So, that becomes 4 K naught A T1 minus T2 by 3L. So, thus we see that if we have a network of thermal conductors, then we can use our current electricity concept to analyze, including the basic formulas of Wheatstone bridge and all such series and parallel combinations to get the desired result.